Today we're going to talk about solving exponential and logarithmic equations. By the end of this video, you should be able to solve exponential equations and logarithmic equations using a variety of methods. First, we're going to take a look at exponential equations. One situation you might end up with is if the two sides of the equation have the same base, or can be written so that they have the same base. In that case, you are going to use the fact that a to the x equals a to the y if and only if x equals y to help you solve the equation. So, our first problem is 3 to the x plus 1 equals 81. One way we could solve this problem is by rewriting it so that both sides of the equation have the same base. 81 is 3 to the 4th power. So now that we have rewritten this equation so that both sides of the equation have the same base, we can essentially ignore the base and just look at the exponents. So if this is true, then we know that x plus 1 must equal 4, and then we can solve that and get x equals 3. Let's look at another example using the same technique. For problem number 2, we have 2 to the x times 8 to the negative x equals 4 to the 3x plus 1. Now, we have three different bases right now, but you'll notice that 2, 4, and 8 are all powers of 2. So we can rewrite these so that they all have a base of 2. 8 is 2 cubed, and 4 is 2 squared. Then we just use the laws of exponents to simplify this. Whenever you have a power to a power, you need to multiply the exponents. And here we need to distribute. Then, since we have two exponentials multiplied together and they have the same base, we can add the exponents. Now that we have 2 to the negative 2x equals 2 to the 6x plus 2, we can apply this rule here and just look at the exponents. So we have negative 2x equals 6x plus 2, and then we just solve. So we get x equals negative 1/4. Let's look at one more example using this technique. Here we have 1/5 to the x plus 4 equals square root of 5. 1/5 is the same as 5 to the negative 1 power. And the square root is the same thing as the 1/2 power. Again, we need to use our laws of exponents. We can multiply our exponents on the left side. And now, since both sides of the equation have the same base, we can just look at the exponents and solve. So we get x equals negative 9/2. Let's take a look at another technique for solving exponentials. You cannot always rewrite an equation so that both sides of the equation have the same base. So if that's not possible, you can isolate the base, take log, natural log, or log base a of both sides, and then use your calculator to figure out the decimal approximation of the solution. So in problem number 4 here, we need to isolate e to the x. So we'll start by subtracting 5 and dividing by 4. Now, we need to take log, natural log, or log base a of both sides. For this problem, it makes the most sense to take the natural log of both sides, because this allows us to use one of our properties of logarithms that we discussed in a previous video. If we have natural log of e to the x, remember natural log is log base e, so we have log base e of e to the x. We know by one of our properties that the natural log and the e cancel out, so we just have x equals natural log of 14. Then if you type this in the calculator, you get that x is approximately equal to 2.639. Let's look at another example. Here we have 2 to the x equals 20. 2 to the x is already isolated, so now we just need to do the log of both sides. And I'm going to show you two different ways to do this. If we take log base 2 of both sides, we can apply the same property that we used in problem number 4, where log base 2 of 2 to the x simplifies, and we just have x. And then if you type log base 2 of 20 in the calculator, you get 4.322. This is the most efficient way to solve this problem, but I'm going to show you a different way because it introduces a slight variation on this method that can be helpful in other problems. If instead of doing log base 2 of both sides, we did common log of both sides, we would then apply some different properties. We know that log of 2 to the x can be rewritten as x times log of 2. Since this is x times log of 2, I can divide both sides by log of 2 and get x equals log of 20 over log of 2, which by the change of base formula is the same thing as log base 2 of 20. So again, we end up with the same answer. Taking common log or natural log of both sides of the equation work the same way and can be helpful for some problems. Let's take a look at another example. If we have 5 to the 3x plus 2 equals 30 to the x, we cannot rewrite 5 and 30 to have the same base, so we need to take log, natural log, or log base a of both sides. I'm going to choose to do log base 5 of both sides. Again, by the same property that I mentioned in the last two problems, log base 5 of 5 to the 3x plus 2 is just equal to 3x plus 2. Now, we still have some work to do because we still have an x on both sides of the equation. So now I'm going to look at the right side of the equation, and I'm going to bring my exponent out in front. Now, I need to get all of the terms with an x on one side of the equation and all of the terms without an x on the other side of the equation. So that means I need 3x and x times log base 5 of 30 to be on the same side. So I'm going to subtract 3x. Now I can factor an x out of the right side of the equation. Now, if I divide both sides of the equation by log base 5 of 30 minus 3, then I have x by itself, and I'm done. If I plug this in the calculator to get the approximation, I have negative 2.256. You could have also done this problem in a very similar fashion by taking common log of both sides. You would have to move the exponents on both sides of the equation out in front. And then your goal is still to get all of the terms that have an x on one side of the equation, all of the terms that do not have an x on the other side. You factor out the GCF of x, and then divide. Number 7 is a little bit trickier. We have e to the 2x equals 3 times e to the x plus 2 equals 0. This problem is actually secretly a quadratic. I'm going to rewrite this. It's e to the x squared. And that comes from our exponent laws. So you should be able to see here that this is really the same as if I had a squared minus 3a plus 2 equals 0. So I need to factor. If you need to write out this quadratic in green to help you, that's fine. If you don't need to, that is also fine. This quadratic would be factored like this. So in terms of this blue equation that we have e to the x minus 2 times e to the x minus 1 equals 0. So then, just like with a regular quadratic, we have e to the x minus 2 equals 0, e to the x minus 1 equals 0. And we can solve each of these equations. So we have e to the x equals 2 and e to the x equals 1. If we take the natural log of both sides, by using that same property that we've used on every problem so far, natural log of e to the x is just equal to x. So we have that x is equal to natural log of 2 and x is equal to natural log of 1. natural log of 2 is approximately equal to 0.693, and natural log of 1 is equal to 0. So those are our two solutions. Next, let's take a look at some logarithmic equations. One method that you can use for solving logarithmic equations involves condensing the logarithm, if possible, converting it to an exponential, and you have to remember to check for extraneous solutions. We did not have to check for extraneous solutions with the exponentials because the domain of an exponential function is all real numbers. Since the domain of a logarithmic function is typically 0 to infinity or something like that, not all values of x can work, so we have to double check for extraneous solutions. I'm going to start with this problem by dividing both sides by 2 so I can isolate the natural log. Then, since we know that natural log is log base e, I can rewrite this as an exponential. That would give me e squared equals 3 to the x. If I divide both sides by 3, I get e squared over 3 equals x. If I type this in the calculator, I get that x is approximately equal to 2.463. If you want to check your solution using the calculator, you can do that. Just make sure you type in the original problem, 2 times natural log of 3 times 2.463, and it gives us a decimal that's very close to 4. Since we rounded, it's not exactly 4. The way that you can check for extraneous solutions without the calculator involves thinking about the domain of a logarithmic function. You cannot take the log of a negative number. So if you plug our solution in for x, you get natural log of a positive number. So we will not have an extraneous solution. Lastly, we have another problem here. This involves a slightly different technique. Here we want to condense the logarithm first, and then we're going to use the fact that log base a of x equals log base a of y if and only if x equals y. And then of course check for extraneous solutions. So let's start by condensing this logarithm. Since we have the sum of two logs, we can rewrite that as the log of a product on the right side of the equation. I can move this 2 to be the exponent. And then I'm going to go ahead and multiply these two binomials together. So I have natural log of 2x squared minus 7x plus 6 equals natural log of x squared. Now, here's where we apply this fact. One of my friends used to call this the Lumberjack Theorem because you chop the logs off of both sides of the equation. So we just have 2x squared minus 7x plus 6 equals x squared. Then we just solve the quadratic. So if I subtract x squared from both sides and factor, I get that x equals 6 and x equals 1. So you can either plug these into the calculator to check for extraneous solutions, or you can just see if either one of them result in log of a negative number. So if I start with 6, I end up with natural log of 4 plus natural log of 9, and then I have natural log of 6, so that one should be okay. If I look at x equals 1, I end up with natural log of negative 1 plus natural log of negative 1. I can't figure out the natural log of a negative number, so 1 is going to be extraneous, and 6 is my only solution. So I have shown you two different techniques for solving exponential equations and two different techniques for solving logarithmic equations. You can decide which one is most appropriate for each problem that you work on.